Alright, so we're going to move on to our final section of the course, and this is about counting, or you could hear it called enumeration as well, but that's just a fancy word for counting. So we're going to start by counting the number of elements in unions and intersections. And there's some nice patterns that happen with these, and we can use them to start doing some problems that help us count. So the first thing is called the addition principle. Let's call this, I guess, I don't know. Let's call it theorem 41.1. Why not? This is pretty obvious, though. So, if you have a set of sets, where your AIs, these guys are all sets, and they're pairwise disjoint. So pairwise disjoint means take any two of them, say AI and AJ, and if you take the intersection, there's nothing in there. And that's for any I and J. So take any two of them, there is no common element. Well, then the intersection, the union of all of the sets has the cardinality of the sum of each of the individual sets. And we can kind of see this. Let me just draw a little Venn diagram. I'll do it with 3 sets, just as a little example. There's not too much to say here otherwise. So here's A1, A2, and A3. Now this isn't a proof. I'm just kind of showing you what's going on. So they're pairwise disjoint, which means that any of the elements don't lie in any of these 3 sections. So they must all be in the individual sections. So let's put a couple in there. Let's put 3 in there, 2 in there, and 4 in there. Then you can kind of see what's going on here. Well, because there's no overlapping elements, all overlaps in this Venn diagram are empty, so I'll shade that in to denote that. Well, then it's kind of clear that the theorem up here is true. So the proof for this one, I guess, is obvious. There's not too much I'm going to say is obvious. But I think that's a pretty easy result to think about. And I want to note that drawing a Venn diagram isn't a proof, but it's a good way of thinking about what the problem is. So let's start with a little bit, not quite complicated, but a little more complicated of a result. So this will be, let's call it, I guess, theorem 41.2. And that is, let A and B be sets. Then, well, the size of the union is the same thing as the size of A minus B plus the size of B minus A plus the size of the intersection. A intersect B. And we can kind of see that with a Venn diagram. Let's draw it. So here's A, here's B. Well, A minus B is all this stuff in blue. So this is A minus B. B minus A is everything in B that's not in A. So this is B minus A. And the intersection is obviously this stuff. In both sets, this is A intersection B. So it's kind of clear just from the Venn diagram that A union B has these disjoint parts. So, if we can show that all three of these sets are pairwise disjoint, then we're good to go. And it's basically by definition. So the proof. So we need to show that the three sets above, and those three sets I'm talking about are A minus B, B minus A, and A intersection B, show that those three sets are pairwise disjoint. If we can do that, we can just use the addition principle. All right, so let's start. Let's consider the intersection of A minus B and let's do B minus A. All right, so clearly, let's call it, I'm going to call this, in fact, C, just so I don't have to keep writing that whole A minus B intersect B minus A. So clearly, the empty set is a subset of C, because the empty set is a subset of every set. So now if we show the other way, we have equality of sets. So, now we need to show that C is a subset of the empty set, which means that C must be the empty set. That's the only way that anything could be a subset of the empty set. So let's go ahead and do it. So we're going to pick an X in C, and we're going to show that it just can't exist. Okay. So, less X be an element of C, then X is an element of A, and X is not an element of B, because it's in A minus B. That's this part here. Oh, sorry guys, I'm going to change this, but I want to talk about the sets, not the cardinality of the sets. So I really mean the sets themselves, not the cardinality. My mistake, guys. There we are. All right. So that's the A minus B part, and it's also in B minus A. So X is an element of B, and X is not an element of A. But this means, look at this. So this means that X is in B minus A. But look at this. But this means that X is in A and X is not in A. We can look at our rules for logical equivalences here. We're just using the commutativity properties, a bunch of and statements together, so we can just move things around. And this here is, of course, a contradiction. One of these guys here has to be true, one has to be false. So there's no way for them both to be true. So it's a contradiction. It's always false. So this is a contradiction. So X must not exist. And thus, C is indeed the empty set. So we're done with that. So we showed that A minus B and B minus A are pairwise disjoint. And I will just say, in the interest of time, similarly to the above, the other pairs are also disjoint. Thus, the addition principle applies. And we're done. Remember, the addition principle says as long as your sets are pairwise disjoint, to figure out the cardinality of the union of them, just find the cardinality of each of them and add them together, which is what we did. Okay, so that's that. All right, and a quick reminder. Well, this joint bit is important because if A and B are sets, then, if you remember, the size of the union was the size of your first set plus the size of your second set minus this intersection, because you counted that twice. So the fact that you can use the addition principle, that's only applicable when the sets are disjoint. So if not disjoint, this must be subtracted. In fact, this is something we can prove. We can use the ideas of sets to prove this. So let's call this reminder, even though we know it and we talked about it, we didn't prove it. So this is theorem 41.3, if you like. And the proof of this, well, all we're going to do is we're going to write A and B as disjoint unions. So note that A is A minus B union the intersection of A and B, and those guys are disjoint. And B is B minus A union the intersection of A and B. So remember that from above, these are disjoint. Each pair is disjoint. A minus B and A intersection B are disjoint. B minus A and A intersection B are disjoint. Now, from above, we know that A union B is the following. Is A minus B plus B minus A, talking about the cardinality of these sets, plus the intersection of A and B. So we know that. But remember, these guys are disjoint, so we can use the ideas of the addition principle on these sets. So, let's go ahead. Thus, we have that cardinality of A is the same thing as the cardinality of A minus B plus the cardinality of A intersect B, and the cardinality of B is the same as the cardinality of B minus A plus the cardinality of the intersection of A and B. So let's rearrange these here so that we can substitute in for A minus B and B minus A. So let's do that. So we get that A minus B is the same as the cardinality of A minus the cardinality of the intersection of A and B. And similarly, the cardinality of B minus A is the same as the cardinality of B minus the cardinality of the intersection of A and B. And we could sub them in to our equation above. We'll just substitute it into here since we solve for A minus B and B minus A. So we get that A union B, the cardinality of that set is, well, it's A minus the intersection plus the cardinality of B minus the cardinality of the intersection plus A intersect B. And hey, look, we have two cardinalities of A intersect B, one positive, one negative, so they cancel out, and we're left with exactly what we want. Cardinality of A plus the cardinality of B minus the cardinality of A intersect B. And in fact, this is called the principle of inclusion and exclusion for two sets. In fact, we can do this. There's nothing special about two sets. The same idea happens when you have more than two sets as well. I won't prove it, but I'll kind of show you what's happening here. So the principle of inclusion, exclusion for three sets. Well, let's draw it out first. So there's our three sets, A, B, and C. They're not necessarily disjoint, but if we're looking at the cardinality of the union of these guys, well, you could say, all right, let's include everything. So the cardinality of A plus the cardinality of B plus the cardinality of C. So let's just put that in now. So that equals the cardinality of A plus the cardinality of B plus the cardinality of C. But then you're like, oh, wait, but we overcounted here. These sections we're going to highlight in yellow, we counted them twice. Well, we counted that intersection twice. We counted this intersection twice. And we counted that intersection twice. So let's subtract off one copy of each. So we'll subtract A intersect B minus A intersect C minus B intersect C. But wait, if you think a little bit more, when we did that subtraction, well, we subtracted off this intersection in the middle 3 times. So we want it to be there. We had it 3 times when we added up A, B, and C, or the cardinalities of them. But we subtracted it 3 times when we subtracted A intersect B, A intersect C, and B intersect C. But we still need 1 copy of it, so let's add it back. So I'm going to color that in green. So we're going to add this back. So plus the cardinality of the intersection of all 3 sets. And again, this isn't a proof of it, but it gives you a flavor of what's happening in the proof. So in the proof of it, we'd have to write down the mathematical statements precisely, but this is what's happening here. We'd have to explain our reasoning a little bit more than what we're doing now. Now, I'm not going to do the proof. I might leave that as an exercise for you guys. So I'm going to omit it, but I'll talk about what's happening. And the nice thing is it's basically the same as what we did in the 2-set case. So we can change our A's to a disjoint pair of sets, A minus B, plus the intersection of A and B. We can do that with our B's. We can do that with our C's. And then replace. So we get all that cool stuff. Oh, sorry, I noticed a typo. I wrote minus here for these guys, but I really meant intersection. So let me fix that. Sorry, guys. So these here should be intersections. I'm going to circle them just so you know that I fixed them. Usual practice. And you do the same type of set manipulation with disjoint sets, and this argument comes out in the wash, which is pretty cool. There are similar formulas for inclusion-exclusion for more than 3 sets as well. Have a play around with it if you're interested. See if you can come up with what you think those formulas might be. So let's do an example. Let's do an easy example first, and then a harder example. So this is example 41.1. All right. So let's say there are 40 students in Math 1401. Let me tell you the following. I'm going to tell you that, let's say 25 students passed the midterms. I'll tell you that 30 students passed the exam, and let me tell you that 5 students passed neither. So, my first question is how many students passed both, and my second question is how many students passed exactly 1. Okay. So let's draw a Venn diagram, and let's put our information in here as much as we can. So again, the inclusion-exclusion is going to help us out. So we know that 5 students passed neither. So I can put a 5 on the outside of our 2 circles. In fact, let's label these circles. We'll use M for midterms and E for exam. Okay. So we have 3 regions left. And we know the number of people in them. Well, there's 40 students in the class. 5 people passed neither, so there must be 35 people in the union of M and E. So we know that the union of M and E is, well, 40 minus the 5 students that didn't pass either is 35 students. Okay. So we can use the principle of inclusion-exclusion to help us out here. So we know that the union of M and E is in cardinality the same as the cardinality of M plus the cardinality of E minus the cardinality of the intersection M and E. And in some sense, this is a pretty easy problem once we realize we have to use that. We know 3 of these things. We know the cardinality of the union. We know the cardinality of M, 25 students passed the midterms, and we know the cardinality of E, 30 students passed the exam. So we just solve for the intersection. No problem at all. Okay, so let's fill in what we know. 35 equals 25 plus 30 minus what we're looking for. And after a little bit of algebra, you should be able to see that 20 is indeed the intersection of M and E. So we know that 20 students passed both the midterm and exam. All right, so for part 2, oh, wrong color. For part 2, we can use the idea of the additive principle. So we know that the cardinality of M is the same as the cardinality of the difference M minus E plus the plus the cardinality of the intersection of M and E. And that'll give us, let me scroll back up here, that'll give us the people in this section, because remember, this section here is, this is the cardinality of M minus E. And over here is E minus M. So if we can figure out how many students are in those sections, add them together, and we're done. That's one way of doing it. And I'll talk about another way just after this. So we can fill in what we know. We know M is 25. We don't know M minus E. That's what we're looking for. And we know the intersection is 20. So after a little bit of algebra, obviously 5 is the cardinality of M minus E. Excellent. And similarly, well, E is E minus M plus the intersection of M and E. Again, we know both. So E is 30. We don't know E minus M, but we do indeed know the cardinality of the intersection, which is 20. So that tells us that 10 is the cardinality of E minus M. And then the question is asking, well, how many students passed exactly 1? So they're either in m minus e or e minus m. They're disjoint sets. So that's easy to calculate. So we're looking for the size of the cardinality of m minus e union e minus m, which is, by the additive principle, the cardinality of m minus e plus the cardinality of e minus m, which is 5 plus 10, which is 15. And note that I can only use the additive principle here because the sets m minus e and e minus m are disjoint. So I don't need to worry about double counting or anything like that. All right, so we answered those questions, which is excellent. Another way to think of it is, for 2, an alternate way, I'll just talk about it really quick. An alternate way, well, we could realize that m minus e union e minus m is the same thing as the union of those sets, m union e minus the intersection, e intersect m. And that's something we proved way back when we were talking about sets in chapter 2. So we know that this is true. And we also know that these guys are, what do I want to say? We could just figure out the size of each of these guys and we'd be good to go. I'll leave that as a little bit of an exercise for you guys if you want to check it using the alternate method. All right, the final example I want to do for this lecture is the following. So this will be example, what was the last one? 41.1, so this will be 41.2. So let's let the set A be natural numbers such that n is at most 201, and I'll write this down here, 2 divides n, or 3 divides n, or 5 divides n. So that's our set A. So it's all numbers at most 201 that are divisible by either 2, 3, or 5. So what I want to do is I want to find the cardinality of A. And we're going to use the inclusion-exclusion principle to help us out here. So let's come up with some intermediate sets to help us out. We kind of have 3 things going on in this set. We have numbers that are 201 or less. That's kind of like our domain, so don't worry about that. But the condition on them is they're divisible by 2, or they're divisible by 3, or they're divisible by 5. So let's come up with 3 kind of subsets of this that aren't necessarily disjoint. That's fine. So let's define A, let's call it A2, which is same thing. So it's your natural numbers such that n is less than 201, but all I care about is that 2 is a factor of n for A2, and then A3 is defined similarly. Same with A5. Maybe I'll write it like this, because you guys can always rewind if it gets a little confusing. but I'm going to define A3 by the same thing, but instead of a 2, it's if 3 is a factor. And 5 is going to be the same idea. It's going to be the same thing, except we care about if 5 is a factor of n. So I'm defining 3 different sets here. Now our goal is to use inclusion, exclusion to find the cardinality of A, which is, of course, the cardinality of A2 union A3 union A5. So that's our goal here. So let's write down everything we need to find, and then we'll talk about how to find it. So we need the cardinality of A2, A3, A5. We need the cardinality of the intersection of A2 and A3, the cardinality of the intersection of A2 and A5, the cardinality of the intersection of A3 and A5, and the cardinality of the intersection of all 3 of them. Okay. So, let's think about this. Let's define a little bit of a function. So, to help us out here, I'm going to define a floor function. So the floor of x, written like this, is the smallest not the smallest, the greatest integer less than or equal to x. So it's kind of like, how do I want to say it? It is, you can think of it like a rounding down function. Let me give you some examples, just so we understand how this works. So the floor of pi, well, pi is 3.14, so the integer just below that is 3. We just always round down. So the floor of, let's say, -5, well, the greatest integer less than or equal to -5 is -5 itself, which is great. Let's do a couple more. What about something like -10.2? Well, remember, it doesn't round to -10. We're rounding down, but down is negative in this case. So the greatest integer that's less than it is -11. And finally, if we have something along the lines of 7.97, that we need to round down to 7. So that's kind of how this function here works. All right, so we have that function defined. That's going to help us out. Okay, so let's figure out if we can decide what the cardinality of A2 is. Well, it's all numbers divisible by 2. So how many are there? Well, the way to do it is we're going to take the number of numbers we have, 201, and we're going to divide it by 2. Every second number gives us a number divisible by 2. So the problem with that is we have this extra number. If it was just 200, we would say there are 100 numbers. But we have this extra one, And we don't want to count that in any way. So this is where we're going to use our floor function. We just care about how many fit into this, nothing extra. So the answer to this is, of course, what is this? It's the floor of 100.5, which is 100. So there are 100 elements in A2. A3 is 201 divided by 3. Every third element is divisible by 3. And that gives us exactly the floor of 67, which is, of course, 67. A5, well, the floor of 201 divided by 5. Every fifth number gives us a multiple of 5, so something divisible by 5. So that gives us the floor of 40.2, which is, of course, 40. Now let's think about this for a second. I want to go back up here. The intersection of A2 and A3, well, it needs to be a number that's divisible by 2 and divisible by 3. So numbers that are divisible by 2 and divisible by 3 are divisible by 6. That's kind of the definition of divisible by 6. So we need to figure out the cardinality of this A6. So again, 201 divided by 6. And you can check with the calculator. That is 30. What's that? 30 carry your 2, 33 point something. Whatever that is, but I think it's 0.6 repeating. Is that right? Actually, it's 33.5. Whatever it is, it's 33 point something. That's the only important part. So that gets rounded down to 33. There are 33 numbers from 1 to 201 inclusive that are divisible by 6. Same logic applies with A2 and A5. This one will be kind of easy to see. This is A10. So the cardinality of A10 is 201 divided by 10. How many numbers from 1 to 201 are divisible by 10? Well, you could do the division here. This is going to be 20.1, which gets rounded down to 20, but that's kind of obvious, right? 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, and then 110, 120, all the way to 200. So that's 20 different numbers. Then we have A3 intersection A5. Well, this is just A15. Let's scroll again. So the cardinality of A15 is 201 divided by 15, and figure out the floor of that. That is 201 divided by 15 is 13.4, which of course rounds down to 13. And then A30 is 201 divided by 30, which is 6.7, which rounds down to 6. Now, the cardinality of what we're looking for, the union of A2, union A3, union A5, so numbers that are divisible by 2 or 3 or 5, well, that's going to be A2, which is 100, plus A3, which is 67, plus A5, which is 40, A2, A3, A5, minus the intersection of A2 and A3, which is A6, so that's 33, minus the intersection of A2 and A5, which is A10, which is 20, minus the intersection of A3 and A5, which is A15, which is 13. So that's all combinations of 2 sets. And then finally adding the intersection of all 3 sets. A30 is, of course, 6. Okay. So now we add these numbers. So what do we got here? Let's add the easy ones first. So 100 plus 40 minus 20. That looks easy enough to do. I'll put some brackets around that. Then what do we have? So I use these guys. This is just doing arithmetic. This isn't anything particularly complicated. Then let's do what? Let's do 67 plus 6 minus 33 minus 13. So that is 120. And this is 73 minus 46, which is 120 plus, well, 73 minus 46 is 27. So my final answer is 147. So 147 of those 201 numbers are divisible by 2, 3, or 5. And we could use the inclusion-exclusion principle to see that. Again, let's just draw a little Venn diagram here just to help us out. And then we can talk about it a little bit. But this is our final answer. So here's A2, here's A3, here's A5. This region here, the intersection of A2 and A3, this is, of course, A6. And note that A6 is, of course, a subset of A2, and A6 is a subset of A3. Numbers that are divisible by 6 are divisible by 2, and numbers that are divisible by 6 are divisible by 3. And it's similar for the rest of them. So this region here, this is, what is this, A2 and A5, so this is A10. And this region here, in green, this is A15. And the region in yellow in the middle, that's A30. So that's what we're doing here. So we're just using the idea of inclusion-exclusion to help us count these sets. And here's a nice Venn diagram just to see what's going on.